Hi, everyone. My name is Bill Philippak. I'm from Micron Technology, and I'm coming to you from Detroit, Michigan, in one of our many customer labs. And today, what I want to talk to you about is a new way to measure signaling margin in your system. It's something we call a vTSA, and Micron is very, very excited about it and think it'll deliver you data faster and be able to give you the insights that you need as quickly as possible. To really understand what a vTSA is, we have to talk about the old way of measuring signaling margin on a system, and then we'll talk about the pros and cons of each approach. So on the slide here, I've defined what a TSA is. A TSA is just an acronym that Micron uses for timing and signal analysis. And this is really our approach to making sure that the memory interfaces are used properly on your system. And we want to make sure that there's proper margin for the usage conditions that you're planning on putting the system through. Our TSAs usually include measurements of a few things. One of them is signaling margin. On the lower right-hand side of the slide here, you can see a picture of a data eye. This is sort of the classic signal analysis that you're probably used to, where we're measuring certain signals and making sure that they have the proper margins to make sure that they don't fail as they're put through different usage conditions. We also measure other things like critical timings compared to our specifications. In the lower left, you can see sort of a measurement of a relationship between signals to make sure that you're not violating any of the rules that we set forth on that memory device. We also measure power supply ramps and power supply levels and make sure things are stable. And we also make sure that the memory device is configured properly on DRAM as through the mode registers. On other technologies, we make sure all the configuration registers are set appropriately for the system and how it's being used. Our traditional approach to a TSA has been what we now call a pTSA, the P meaning physical. This means we connect test equipment up directly to the system and measure the memory interface. In the lower right-hand corner, you can see a picture of a pTSA. There's an oscilloscope connected up to the system. The system in this case is an NXP i.MX 8 Quad-X Plus MEK. And you can see in the zoomed in picture that we've got the LPDDR4 device removed and we stuck an interposer in between the system and that memory device. And then we've got probes connected to some of the pads and we're directly measuring some of those signals. So requirements to perform a pTSA, first of all, we need to be able to do rework. This means we remove the memory device of interest, we clean up the board, then we add an interposer in between the memory device and the system, and we solder those all back together. Next, of course, we need to have the interposers themselves. Sometimes we have to use sockets to be able to clear some of the other devices on the board. And then, of course, we have to have high bandwidth oscilloscopes and probes and probe heads to be able to measure the signals themselves. So although we can measure the memory interface directly, there are some pitfalls with the pTSA approach. The first is that you have to have expensive test equipment available to be able to do the measurements. And then the next thing is, even if you can do the measurements, the fact that you have to insert test equipment in the first place means that you are impacting signaling itself just to be able to observe it. We try to make interposers and sockets and so on as transparent as possible, but of course they aren't fully transparent and they are having some impact on the signal. As mentioned, we have to perform rework to be able to get the test equipment hooked up, and rework always comes with a risk. Again, we have to remove components, we have to solder components to interposers. There's always risk of damaging the system or the memory device when we're doing this kind of rework. The next issue is that it's very, very time consuming to take measurements in a pTSA. As you can see in the picture, we've got 2 probes soldered down. This will give us data on just 2 signals. If you can imagine trying to do this and then set up the scope and take the measurements that you need across the memory interface, it's going to take a very, very long time. Today, we're only taking data on a subset of the memory interface, and it still takes us a couple weeks to complete a TSA between the rework that's required and the measurements themselves. Imagine if we were going to try to do that across the entire memory interface. It's just not really feasible. So let's talk about a better approach. This is what we call the vTSA. The V in vTSA stands for virtual. And usually when you hear virtual, you think we're talking about simulation. In this case, that isn't true. What vTSA is using the controller's built-in capabilities to test margin data itself without hooking up any test equipment. So let me explain what that means. Even today, to operate a modern memory device, a controller has to have the capability to shift the delivery of signals, shift strobes, change reference voltages, change termination settings, and so on to be able to optimize for the system. To go one step further, most controllers go through a training algorithm where they're actually sweeping all of these parameters to figure out what the best operating point is for that system. Now, since this training is already being done, that means the controller already has information about the signal margins on that system. It's just that once it figures out the operating points, that information is being thrown away. What a vTSA does is provides an interface that allows us to collect that information and study it to figure out what the signal margins were and figure out if that's going to be enough to support the usage conditions of interest. So on the right-hand side, you can actually see an example output from a vTSA, and we're going to dive into this in more detail. But this output shows you just an example of what vTSA provides. The green region is essentially a data eye. It shows you the area in terms of time on the x-axis and voltage on the y-axis where you had a passing result, and the black area is failing. And then the little point in the middle, the little black point, is the point at which the controller chose to operate. Normally, a system would only store that black point in the middle to say that that's where it needs to operate after performing training. The vTSA simply captures the rest of the data to show you how much margin you had around that black point. So what are the advantages of a vTSA? Well, the first one's pretty obvious. I didn't have to use any test equipment to gather this kind of information. So all of the downfalls I talked about before about inserting test equipment in terms of impacting the signal, having to perform rework, and the risk associated with that, those all don't exist for vTSA. The other advantage is it's much, much faster to collect information like this from a vTSA compared to a pTSA. I can collect information across the entire memory interface, meaning every DQ, every command address bit, in a matter of minutes compared to what it takes on a pTSA that might take weeks or months to do something like that. So what I'm going to do now is I'm going to give you a demonstration of the vTSA tool so you can get a grasp for what they look like and what kind of information they provide. To do this, I'm going to use an NXP i.MX mini evaluation kit. This kit has an LPDDR4 device from Micron on it, and we're going to use it to run the vTSA tool and show you what it looks like. And after that, I'm going to show you a comparison between the results that I got from the vTSA, and I'm going to compare those to results that I measured directly on this same exact board doing a pTSA. So I'm going to hop over to the vTSA tool now and show you how it works. Okay, so here we are in the DDR tool. If you've ever worked with the i.MX mini platform, you're probably very familiar with this tool. First thing you got to do is set up the board in serial download mode so that it works properly with this tool. And then you've got to select your COM port down here. COM7 happens to be the one that works with my computer. So you set that up correctly, and then you can run this tool to make sure that things are working properly. This is a very simple init test. We can run that just to make sure communications are as they should be. I already ran it. You can see here we're passing that test, so we can move on. The thing we're most interested in here is this diags tab. If I click the diags, I have two options. One is write margin, and the next one is read margin. So these two tests are going to run the vTSA tool itself. The write margin is when the i.MX mini is writing data to the LPDDR4 device. And what it's going to do is it's going to skew the delivery of those signals in time, and it's also going to adjust the reference of the receiver on the DRAM side through mode registers to paint the data eye and give us results to show us the signaling margin. On the read side, the LPDDR4 device is the one outputting data, and the i.MX mini is then changing where it strobes that data and also changing its reference for its receivers to paint the data eye and show us what that looks like. One advantage to a vTSA compared to a pTSA that we'll talk about again later is the fact that I can actually do an accurate read margin measurement using a vTSA. The reason is that I have control through the tool of parameters that are on the controller side. On a pTSA, I'm measuring everything on the DRAM, which means I'm not going to get accurate results for what the read eye looks like. Here I can get accurate results because I'm modifying parameters on the controller itself. Okay, so as an example, I'm just going to go ahead and run the write margin. And all you do is check this box and hit start validation, and it'll go through and run all the characterization, which again is basically the training routine, but saving off the data. And then it's going to show us results in this window. I'm going to go ahead and press start, and then I'm going to come back when the results are ready, and we'll talk about what they look like. Okay, so the run is complete, and we have our results here. It took about a minute to run, so not very long, but I didn't want you to sit through it, of course, but very fast compared to what it would take to do this physically. So let's focus on one of the graphs here just to walk through what we're seeing. Let's focus on this upper left. So here we have DQ0, and what you're seeing is on the x-axis, this is the time delivery of the signal. So the controller is skewing when the signal is delivered to the DRAM, both negative and positive. And then also on the y-axis, it is changing the reference voltage, basically what determines a 1 versus a 0 on the receiver on the DRAM side from a low value to a high value. And that essentially is painting the data I. And what you see here is the green portion is where you got back the data that you expected, the data that you wrote. So this is passing, and the black region is where you had failures. And then this little black dot in the middle, as I said before, is the point that the controller chooses to train itself. This is the point that it wants to use in terms of time delivery and the voltage reference to set the DRAM to. So then if I scroll around, you can see that I have one of those data I's for every single DQ on the system. There are 2 channels on this particular system, and you can see each of those data I's for each of the DQs. So I get all the information about what each DQ looks like, and I can compare each one to figure out which one's my worst case, make sure none of them have a collapsed data I that might cause problems in the system. I could run this characterization at different temperatures and so on to understand the difference, and I'm getting all that data real time within about a minute. So you can use this graphical tool to compare each of the DQs together. There's some tooltips to help you figure out what each data I looks like. Or there's options to dump this data out and use an external tool to parse it. So that's what I've done, and I'm going to show you what that looks like here, and then we're going to compare it to a physical TSA result. Okay, so all I've done here is I've taken all that same data out of the vTSA tool from the right characterization that we did, and I plugged it in so I could do an overlay. And that's what these 2 plots are showing. The left one is channel A, the right one is channel B. And then in the charts at the bottom, I have a measurement of each of the data I's. Now you can measure data I's in many different ways. You can do it in terms of the time and voltage margin. Here I chose to do it based on area, but you can do it in many different ways. And what I'm showing here with the colors is just a characterization of how wide those data I's are, and you can see which ones are worse and which ones are better. So this is very, very useful information, especially if you've got simulation results to compare to or are looking for marginalities. This is going to be really helpful for you. One word of caution is that the naming convention of the DQs on the controller side may not be the same as the DRAM side. We call this swizzling if they are remapped, and that's done for board layout reasons. In this case, that's exactly what happened. You can see an example down here where we have the vTSA telling us that we have DQ0, but in fact that is DQ8 of channel B on the DRAM. And again, this is just from swizzling. It's not a problem. You just need to be aware of it so you know what DQ you're actually measuring. Okay, so now let's compare those results that we got out of vTSA to if we measure them physically. So what I did is I took this exact same EVK and I did a physical TSA on it. That means I did all of the rework, I put an interposer down, and I probed these signals to see what they look like. So I chose to do this on what's called DQ18 in the vTSA, which maps to DQ3 of channel A on the DRAM itself. So the vTSA result is in blue, and the red result is the physical measurement itself. And you see that the measurements are very, very close. It's within about 5% if you consider area as your metric. I consider this to be a very, very close match. If you remember, the physical TSA introduces test equipment, which has some impact on the signaling. Also, the physical TSA has no concept of whether the receiver is going to judge something as a 1 or a 0. We simply compare it to a spec and say, we know that this might become a problem, so this is how wide the data I is. The vTSA actually truly measures pass-fail, meaning it measures when the bits flip from a 0 to 1 or a 1 to 0. So in that way, a vTSA is actually more accurate. But given those differences, this is a very, very close match. So in summary, the vTSA approach gives you access to information about signaling margin on your system in a very quick and easy way. A number of NXP platforms support vTSA tools. The i.MX 8M Mini platform is one of them that supports it, as I showed today, but there are others as well. And we at Micron really think this is an important tool to be able to give you access to the information you need quickly and shorten your learning cycles so that you can understand if you have marginalities early on in the process and get those addressed before it becomes a bigger problem. pTSA is a direct measurement in the memory interface, but it has its pitfalls: time, complication, and sometimes accuracy. vTSA is able to deliver the most critical information to you very quickly without much effort, so we find it to be a very useful tool and hope you'll consider using it in the future. Thank you very much for listening to this presentation. If you have questions or comments, feel free to reach out to us. Thank you.